So, now we will go to Green's function, continuation of Green's function. Okay. So, in the last module I had worked with Poisson equation, right. So, we computed the Green's function for Poisson equation. Now, we will do some more. So, Helmholtz equation, okay, you will find this in this course. So, what is Helmholtz equation? This is wave equation. Well, I am going to derive Helmholtz equation, okay, just give me 1 minute. So, this is a wave equation, no, partial. So, this is time derivative. When I write like this, is a time derivative d, this is equal to d by dt of some function. If I write like this, this is partial with x, okay. So, this means double derivative in time, and c is the speed of the wave. So, so this is the double derivative in time minus Laplacian phi x t. Now, the right hand side I am going to assume that functional form for time, okay. Is function of x, it is rho x, but the function of time is exponential I omega t. So, imagine that there is a reduced station which is transmitting a wave with frequency, fixed frequency, which is I omega t, with fixed frequency of frequency omega, okay. So, my source will be e to the power I omega t times rho of x, okay. A reduced station is not a point source, but okay, there is some kind of there are a lot of charges which are transmitting electromagnetic field. Is that okay? Now, if I have this kind of source, this source, right, I said this is source. If this kind of source, then for the steady state solution, we are not going to deal with transients in the beginning part to satisfy the initial condition, all that I will ignore. The steady state solution, if you wait for long enough time, then the steady state solution phi x t should also have e to I omega t response. The time dependence will be e to I omega t, okay. This is something very similar to what we do for oscillators. If I force an oscillator with certain frequency, then the response under steady state will be e to I omega t except at the resonance, okay. But we are not going to have resonance for, well, we will ignore resonance, okay, that special condition we will ignore in this stuff. So, my response also is e to I omega t. Now, plug that in here. If you plug that in here, what do you get? So, this one will give you minus omega squared, no. If I put e to I omega t for here. So, what I am going to do here, I just plug in e to the power I omega t phi f x. So, double derivative of that will give us minus omega squared, and Laplacian will give us plus k squared, and there is c squared sitting here, fine, straightforward, and we call this omega squared by c square as k naught square, okay. Okay, these also minus sign, they are both the minus signs, this is well, this is plus actually, okay. No, so I have right now put Laplacian, I am not substituting here, this is Laplacian. So, I have not put k square right now, this is Laplacian, because phi of x, phi is function of x. So, do not disturb phi of x or Laplacian, just keep it like that. So, this becomes minus Laplacian and minus k square. So, minus sign I send it to the right hand side, okay. So, this is my equation, this is called Helmholtz equation, okay. We gotten rid of time dependence by assuming that my wave my source is of the form e to I omega t, okay. So, now what is the Green's function for this? So, rho of x I am going to assume a delta function, okay. Then I get the Green's function, and I did not write it, but you can easily see what should be the Green's function in Fourier space, yes. So, let me just write down for completeness Laplacian g of x prime delta x minus x prime, okay. Now, when I do the Fourier transform, then e to the power I k x or k dot x will give me minus k squared, this guy will give minus k squared, and this is my Fourier transform of the Green's function g of k, okay. This bit of algebra, but I can't do every step. You should be able to see that this will be indeed the Green's function, okay. Now, this is in Fourier space in any dimension. This is the beauty of Fourier space, in these formulas that work in any dimension. Now, I want to go to real space. Okay. So, let us work it out for 1D. In field theory often we will not work with 1D, we will work with 3D, okay, typically, but let us do it for exercise, let us do it for 1D. So, my Green's function is this is a Green's function, right. So, I want to get to real space. So, by definition g of x is dk by 2 pi, like d is 1. So, this is dk 2 pi, this stuff. So, I am integrating along this line. Now, there are singularities sitting at the x axis, right, k naught is real. So, the two singularities sitting there, k equal to minus k naught and k equal to plus k naught, right. So, this is k axis, real k. Now, that is a problem, something pole sitting on the axis is a problem. Okay. Now, that is where we invoke boundary condition. So, I will say that I am looking for waves which are going right, well, my source is transmitting waves, outward going waves. So, my source is here and it is going to transmit waves both left and right. Okay. So, I am going to choose my waves which are going to the right in the right hand side, x greater than 0, x greater than 0, and left for x less than 0. Okay. These to illustrate the power of shifting the poles, that is in my hand, because my boundary condition is not specified. So, I am going to specify boundary condition by shifting the poles. Okay. So, I am going to shift the pole, the right pole upward and the left pole downward. Okay. Now, I am going to do the closed loop integral. Okay. Closed loop integral means I need to close the contour. So, which side of the contour, upper plane or lower plane I should choose, so that my semicircle should give you 0, right. I want this integral over a semicircle to 0, to go to 0. By Jordan lemma, since k is positive and x is also positive, well sorry, x is positive not k, x is positive, right, x is positive, k can be negative or positive, okay, or k is a complex number. I am extending my k to be complex because it is going in the full complex space. So, x is positive. So, since x is positive, I will get 0 if I choose my semicircle in the upper half, right, Jordan lemma, we did that. So, I close from the top. Okay. So, what is the contribution from, so the closed loop will be not 0, because there is a pole inside. Okay, 2 pi I integrate that at the function. Okay. So, this algebra I am going to leave it to you, you should work it out. So, do the closed loop here, this part will give 0. So, let me just do it the sketch, this part. Integral has, from normally people use this gamma, integral gamma plus g of x, right. This is g of x and the integral will be gamma, this is 0. Okay. This must be equal to the Cauchy theorem, 2 pi I value of the function at the pole. Okay. Now, look at here, this part. So, we write bottom is k naught minus k, k naught plus k. So, pole is at k equal to k naught, this is k naught plus epsilon. Okay. So, pole has been shifted, but epsilon is small, tiny. So, this is pole is coming here, but it is k naught minus k. So, I need to flip it, remember it is z minus z naught. So, I need to put a minus sign and put k minus k naught, k plus k naught. Okay. So, pole contribution will come from here. Okay. So, there is a minus sign, you pull it out, okay, put a minus sign here, and then value of the function at k equal to k naught. So, what will I get? E to power I k naught x. So, this is k is replaced by k naught and here also k is replaced by k naught. So, divided by 2 k naught, okay, and there is 1 by 2 pi sitting there, 1 by 2 pi, this 2 pi is also sitting there. So, this 2 pi cancels and I get minus I exponential I k naught x by 2 k naught. Okay. So, that is my Green's function. Is that clear? Okay. Now, this is the space part, but now recall what was the source. Source is e to power I omega t, then delta function. Okay. That was source. So, my response is this, but my source e to I omega t will be the same. Oops. Well, I am using here minus I omega t. Okay, this is all hidden there. So, my source I am using is e to power I omega t, e to power I k naught x. Okay, is red is cancelled. So, I am using my source to be e to power I minus I omega t. Okay, that to make sense, and that will also give you minus omega squared. So, this k naught square will come for both e to power minus omega t as well as e to power plus omega t. Okay. So, this is a wave going to the right. Is that correct? This one. Now, for x less than 0, what do I do? For g x less than 0. Now, here imagine this x is less than 0, negative. Now, which side should I close the semicircle? Bottom, right, because x is negative, Jordan lemma again. So, I close it from bottom and do the algebra, then you find that my answer is this. Okay. I recommend that you do fill this algebra, it is straightforward, but you should do that part, and my wave will be looking like this, e to I k naught mod x minus omega t. Okay. Now, is it which way the wave is going for x less than 0? Is it going like that or is going like that? It is going backward because mod x is positive number. So, imagine I go from here to there. So, mod x is increasing when I go from there to here, and time will also increase that way. So, my wave is, this is the wave which is going that way. So, my Green's function, by choosing these poles like this, the right pole above the axis and left pole below the axis, I am able to achieve my waves which are going away from the source, right. So, radio station is a 1D radio station, okay, which is transmitting waves this way and transmitting wave this way all the time. Okay. So, that is the difference. It is not delta function in time, you see e to I omega t or e to power minus I omega t in time. Okay. So, this 1D straightforward, right. What happens in 3D? Okay. So, 3D, of course, I need to integrate in 3D. So, this is a really a source which is e to power minus I omega t in time, but point source in space, like a charge. Okay. Charge is oscillating continuously, exponentially in time. Well, oscillating in time, oscillating in time. Okay. So, imagine there is a charge which is oscillating like that. So, this is really antenna, 3D antenna, but it is a point source antenna. Okay. Now, the Green's function is exactly the same as before, but now I need to do integrate it in 3D. Okay. Now, you need to follow exactly same steps as what I did for Poisson equation. You can choose your r to be along the z axis, r vector, and I need to integrate over k. Okay. So, by the way, this, okay, so you just follow the same steps. Okay. Now, I have some steps here, I will not do it in detail, but you can just do it yourself. So, this k dk will, in fact, there is a k square dk, but there is a one k will come from here, k square dk, this is cancelling here. So, that k dk, there is a 2 pi coming from d phi integral, that will cancel cube to 2 pi square, and now there is a d theta integral which I did in the last class for Poisson equation. D theta will give us e to I k r minus e to power minus k r by 2 I k r. Remember, this was sum of e to power I k r cos theta, d cos theta. Okay. So, it comes like that. Now, this nice trick, this function, okay, the negative part e to the power exponential minus I k r, you make a change of variable minus k to k. Okay. So, this is a k sitting here and this k square does not change sign. So, this minus will get absorbed by this minus k, and you can go from 0 to infinity, rather transform this integral from 0 to infinity to minus infinity to plus infinity with only one term e to the power a k r. It is a nice trick, just change a variable for this part. Okay. Now, this is nice, right? I mean, you always convert minus infinity to plus infinity, okay. Try to do it. Sometimes, well, we will not do that kind of integral, but branch cuts when you got, then there is a problem, okay. Branch cuts we will not do in this course, okay. That is also very nice and cute integrals, but we will not get into that. But otherwise, you can typically manage to get minus infinity to plus infinity. Now, this integral is pretty much similar like what we had in the last slide, okay. This k sitting here, that is the only difference, right. I mean, otherwise it is same as before, okay. Again apply the contour, r is always positive, right, r is a magnitude of r, so it is positive. So, I close from the top, and you do the algebra, and the answer is this exponential I k r by 4 pi r. So, this is the in fact amplitude of the electric field. Well I mean, okay, electric field is a vector, but you will find something like this when you potential will look like this e to I k r by 4 pi r. Anyway, this is a Green's function in real space for Helmholtz equation, okay. This is a pretty simple derivation in 3D. We need some of this stuff when we get into the real field theory. Now, a related problem is this: instead of k squared minus k naught square, I have k squared plus m squared, okay. Now, we can follow the same scheme. Where are the poles, by the way, for this? It is in the imaginary line. Here I do not need to shift the poles, it is already in imaginary line, plus I m and minus I m. We follow exactly the same procedure. In 3D, g of r is this exponential minus m r by 4 pi r, okay. This is the shielded electric potential, or in field theory m is like mass, okay. So, when I do the field theory with massive particles, we will get this Green's function, okay, and then this will be the real space Green's function. Now, one more point I would like to mention, that this g of r is not dependent on the direction of r, right. It is a scalar function, it does not depend on which direction is r, this way, that way, it is a same same formula. So, it is basically scalar g of r, okay. So, we should also notice that, okay. Now, let us go to slightly more complicated thing, wave equation. I can take a break here. Any questions on or what I did so far? It is all clear, no? I mean, this bit of mathematics, who does not follow these steps? Anyone is not following it? Or who is bored with this algebra? Just raise your hand. We will edit this part, of course. So, your face is anyway not being shown, okay. So, you do not hesitate. Are you bored with this, or if not, I mean, it is good mathematics, no? I mean, this is something which should learn, but we will need it for this course, I assure you. And E and M, somebody pointed out, electrodynamics, you have all this stuff in your course. How many of you are doing E and M right now? Anyone? No. Okay. So, let us go to the next step, wave equation. So, this is the same equation which I wrote in the last stuff, but we have its source. A source is that antenna, no, that is the source. But now, this rho will be a delta function in time. So, it is a pulse. Imagine the electron just blipped, okay. It is not oscillating continuously now, it is just a blip, electron just jumped like that, okay. So, at time t. So, I am going to say that my source is delta x minus x prime, this is source at x equal to x prime. and in delta in time at time t prime it did this blip. Or you can think of you threw a stone in a pond, that will create waves, but there is a point source in the pond at time of the impact. Okay. So, that is the source. So, you are going to generate waves which are travelling outward. It is not a continuous wave which is going on forever, this front will just move forward. Okay. So, what is the Green's function for this? So, now I need to use a 4 dimensional Green's function, right, e to by I k dot x minus I omega t, because there is a time variable sitting here as well. So, this is what I need to use. My function, well, I mean this is a general formula which I had written in the in previous slides. So, my Green's function will be function of k and omega. Okay. So, I plug g k omega. In fact, I instead of phi just put g here, okay, and I assume t prime to be 0 and x prime to be 0. Okay, that is for convenience, otherwise I have to carry this x prime t prime. So, I plug this here, and the right hand side is we write as a delta function, this divided by dk d omega by 2 pi to the power d plus 1. Okay, and assuming the completeness of basis and orthogonal basis, we get this formula. G k omega is k squared 1 divided by k squared minus omega squared. Here k is a variable and omega is a variable, both are varying. In the Helmholtz equation, for me k was variable, but omega was not there, it was k naught square. But now my omega also is varying with omega is also variable. Okay. So, that is why I am going to get g is a function of x and time. Okay. So, first we will do the time integral or d omega integral, which will give me a function of time. So, I am wanting to get g k of t. Okay. Only thing is, of course, for my slide I am not writing it, so things tend to move fast, but I am going slow, and please remember this, it is coming below k square minus omega square, and the signs are different. One is positive k squared, omega is negative because of this one, this minus omega square, and Laplacian gives you plus k, minus Laplacian gives you k squared. Okay. So, this from the structure, and you can guess that pole will be at k equal to omega, that kind of. So, is going to, so that is what we get here. Now, let us do the, okay, this part is okay. Now, so I do this time integral, okay, g k tau. From here I am going to do d, so keep k as is, but it do integrate what omega, right. So, d omega by 2 pi, this comes here, e to power minus I omega t, it is not plus, it is a minus, and this integral needs to be done. Now, we have two poles, right. Here omega is a variable, but k is not. So, where are the, so this omega real, okay. So, the poles are at plus k and minus k. Now, it is minus I omega t, so I need to close from the tau is, well, depends on tau positive, tau negative, tau can positive and negative both can occur. So, this algebra I will leave it for you. Okay. So, for tau positive, so I am going to shift the pole, okay, I have to shift the pole downward actually, in fact, and do like this for tau positive. So, tau positive I should close from the bottom. Okay. So, similar contour integral, so that the semicircle is 0 and we get the contribution from both the poles, and it is not e to the power I k t, is sin k t, means I am getting contribution from both the poles. Okay. Now, this is by choice, I am in fact I am looking for a solution which is there is a there is a, if there is a pulse here, then it should propagate both sides. Okay. This by, in fact, I know the answer, what should it look like, and that is where I am tweaking my poles, is I am doing the trick. If you do not do that way, then you will get probably a wave only going to the right front, which is not sensible. I want wave to go both sides. So that is what I think this boundary condition is not imposed well, we just choose poles by, sorry, you impose the boundary condition by shifting the poles. Okay. So I get this by shifting the poles, and this by g k t, okay, sin k tau by tau. Now I am going to do the k integral, right. I just integrate k part. So this was omega part is done already. Now I am going to do the k part, do in 2 steps. Of course, if you want, you can do in one step all of it, but it is good idea to do it separately, that I find it easier to manage. Now, so this is g k tau e to power I k dot r. So this is what I written here. No, so I am going from k space to r space. Okay. Now g k tau is sin k tau by k. Now this formula is valid for any dimensions, 1D, 2D, 3D is all valid. Okay. So let us look at 1D first. This same formula I like. So in 1D, this exponential will be e to power a cos kr plus I sin kr, correct. Now what happens to sin kr? So sin kr by k, sin kr by k sin k tau, no odd, there sin kr by k is even, but sin k tau is odd. When I change sign from positive k to negative k, I will get exactly opposite. So this part integral will go to 0, imaginary part. What survives? Only the real part. Okay. So now the real part, in fact, if you see it, we can, well, anyway, let's look and do in 2 steps. I use the product formula. So if I use the product formula, I will get sin k tau plus r plus sin k tau minus r. This you know, right, sin cos is sin a plus b, sin a, well, sin a cos b twice is sin a plus b plus sin a minus b. Okay, I just use this formula. Okay, trigonometry. Okay, I do not know how many of you remember this, but this is a trigonometry formula. So it gives me that. Okay. Now this integral has this is a homework problem. Sin ky by k dk is a sine function, pi times sine function. That means sine function is, now this is doable by the tricks we have done in the past, by shifting poles and well, you can do this part, struggle a bit with this, but you can show it. So sine function is for y positive is 1 and y negative is minus 1. This is sine function of y with y. So y positive is 1 and y negative is minus 1. Theta function is y positive is 1 and y negative is 0. Sine is combination of the two. So this is a nice function, and we need this here. So I get sine, the k here and dk there. So this will be combination of sines. So I get sin tau plus r from here and sin tau minus r here. Okay, sum of the two sines function. Now you can just play around with this and you will find this to be half for minus, there is a 2 will come here. So minus t to t will get half and 0 otherwise. So what we get here is like that, is a function of time. This is 0, this is t and minus t, and this value is half. This is my g of r. So It makes sense? You may not be able to guess half, but this is a front. So, I did some shaking up in the at the origin in 1D, and this front is just going both sides. In 3D is like a spherical front, but in 1D this is what we get, is like a, it covers that region. It is not that we get delta function in both left and right. In 1D we get basically this 1D space is all covered, it keeps moving like that in both sides. 1D, 2D, 3D, they have very different properties. Like potential for 1D we saw that it goes linear in X for Poisson equation. That is like capacitor plates, electric field is constant and the potential is linear. In 2D it is log and in 3D is 1 over r. Okay. And you can also argue why it should be so by various physical arguments, but this is the front which is covering in the region. Okay. It just follows from mathematics as well, but I will not delve into physical arguments. Okay. So, this is 1D. So, wave front propagating in both minus and positive direction, and this happened because I chose the poles appropriately. I had shifted poles, both the poles in my omega integral. Okay. Now, it is just algebra actually, I think I will not okay, you can fill up the steps, but this is what we get. In 3 dimensions pretty similar algebra, and this d cos theta da 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 da. So, here again I use the product rule, okay, and I get in fact there is no 1 by k here, okay. So, it is not a sine function anymore. What is this stuff? Integral dk, this one. So, what will this guy? Cos k times a positive number, this is a positive number, no? Integral of cosine 0 to infinity cos k times a dk. Well, I am going to infinity, huh? You can make it minus infinity and half if you like. It is an even function, so I can divide by 2. So, what is cosine integral? The cosine k of a, k times a dk, a positive, it is 0 unless k equal to 0. If k is 0, then it is infinite, but if k is not 0, cosine will cancel, no, I mean this is just straightforward, positive and negative will just cancel. Okay, so, it is a delta k equal to 0. Okay, so, basically this integral gives you 0, and this will give us non-zero value when t equal to r, delta function, no, that is the delta function. So, that is the next step, delta t minus r divided by 4 pi r. Okay, there is a pi coming from this dk integral, that pi cancels with that. So, this is the front. Now, it is a delta function front. The front is not, so we get a delta function which is moving outward. So, there is a blast at origin, then that will create a front. Of course, inside there is no g is 0 inside and z 0 outside, only at the front it is non-zero. Okay, so this solution is different, but this is a proof.